Hi guys, this is Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland. And this short video is going to deal with the application of the standard normal transformation. Okay, so what we're going to concentrate on is the standard normal transformation. Okay, and let's just, I suppose, familiarize ourselves with the transformation formula. Transformation formula says that z of x is equal to x minus mu all over sigma. Okay, and what we use this transformation formula for is to shift and to bend a population that has a particular mean value mu and standard deviation sigma, okay, into a population that has a mean value of 0 and a standard deviation of 1. Okay. That might sound a little bit cryptic there, okay, so let's actually just look at this particular scenario and try to understand what we're trying to do. Okay, so factory workers have average earnings of 660 euros, and we know that these earnings have a standard deviation of 35 euros. And in this question here, we're being asked, if an employee is chosen at random from this particular population, what is the probability that the employee earns between 692 euros and 725 euros? Okay, so the first thing that we'll always do is try to understand the population that we're dealing with. And to understand the population, what we should always ask ourselves is, what are the population parameters? What are the population mean? And what is the population standard deviation? So in this case, we know that factory workers have average earnings of 660 euros. So the population mean is equal to 660. Mu is equal to 660. That's the mean value of the population. And the standard deviation is equal to 35 euros. So sigma is equal to 35. Sigma being this population standard deviation. Okay. So what we know and what we're going to assume in all of these cases is that the population is normally distributed. So because we're assuming normally distributed population, we can I suppose represent this particular population through a curve. Okay, so what we know now is that this population is represented by a normally distributed curve. It's a bell-shaped curve. Okay, and because of the properties of these bell-shaped curves, they're symmetrical, and the center point, which is our measure of center here, is always going to be down the center of this particular curve. In this situation, the population is centered on 660. So 660 is our center point here. Okay? And it has a standard deviation of 35 units, which tells us how skinny or how fat this particular distribution is. Okay. So this is our population, or this curve represents our population. And all observations, all factory worker earnings are listed along this horizontal axis. This 660 here represents factory workers that earn 660 euros. So all of these earnings are along here, so this axis represents our x-axis, which is x is the variable associated with factory worker earnings. Okay. Now what we're interested in is we randomly select somebody from this population. We're being asked what is the probability that the employee randomly selected earns between 692 euros and 725 euros. Okay, so 692 on this particular axis here is going to be to the left hand side of 660. So 692 is going to be around here, 692. Okay, and 725 is also going to be to the, it's going to be to the right hand side of 660. Okay, 692 is to the right hand side because it's greater than 660, and 725 is also to the right hand side of 660, which is in around here. Let's say 725, it's greater than 692 and it's also greater than 660, so it's going to be over here. Now what we're interested in is what's the probability that the employee selected at random earns between 692 and 725. This basically equates to a question that's asking us, what is the area under the curve between those two values, 692 and 725? Or more importantly, what is the probability that if we randomly select a single worker from this particular population, okay, that they earn between 692 and 725? Actually, I suppose I'd be better off doing this like this, that the person selected earns more than 692 and less than 725. Okay, so what's the probability that the person selected at random earns more than 692 and less than 725? Okay. Now what we know that what we should always do is we should always apply our standard normal transformation to all values that we have listed along this horizontal axis. In this case, there's three values. There's 660, 692, and a 725. But we know that the center point of our distribution under the standard normal transformation is always taken to 0. So z, when x is equal to 0, is equal to 0. Okay, so we know that. Okay? So where does 692 go to? Well, let's try that. So z, when x is equal to 692, is equal to, well, x is 692. Okay, so x is 692. So it's 692 minus the population mean, which is 660, divided by the population standard deviation, which is 35. And that gives us a value of 32 divided by 35. Okay. Now when we have a look at this on our calculator, we have 32 divided by 35 gives us a value of 0.914. Now we know that our tables only give us probabilities to 2 decimal places, so we'll round this to 2 decimal places, which is equal to 0.91. Okay, so under the transform, 660 is taken to 0, okay, and 692 is taken to 0.91. So our third point is 725. So where does that take into under this transformation? So let's try that. So z, when x is equal to 725, okay, it's going to be equal to x, which is 725, minus the mean, which is 660, okay, divided by the standard deviation, which is 35. Okay, so when we take this away, when we take 660 away from 725, we're left with 65 divided by 35. Okay, so let's have a look at that particular calculation there. So we have 65 divided by 35 gives us a value of 1.857, and to 2 decimal places that's equivalent to 1.86. Okay, so under the standard normal transformation, our three values have been taken to x. When x is 0, it's been taken to 0. When x is 692, it's been taken to 0.91, and when x is 725, it's been taken to 1.86. And we know that this transformation bends this curve into the standard normal curve. So what's after happening here is that these values now have been transformed onto the curve that's a standard normal curve. 660 went to 0. Okay. 692 went to 0.91. Okay. And 725, which is here, went to 1.86, which is over here somewhere, 1.86. And these values are z values, or they're associated with the standard normal variable z. So this axis here represents the z-axis. Okay. In our original scenario, we were interested in the area between 692 and 725. In this scenario here, we're going to be interested in the calculation of the area between 0.91 and 1.86. Okay. So what we know is, and what we should always do, is that when we have positive z values, that we should look them positive z values up on our tables. Okay, so I'm going to look them values up on our tables. Okay, and I suppose what we're going to look up first is 0.91. So let's have a look at when z is 0.91. We know that the first significant digit and the first decimal digit are listed down the first column. So we're looking for 0.90. And the second decimal digit is 1, so we're going to come across to 0.01. Okay. With respect, so we're looking for this value here on our tables. With respect to the second value, its first significant digit is 1, and its first decimal digit is an 8. Okay, so we're going to come down to, I suppose we're going to come down to 1.80 on our tables. And we're going to come across to the column that's labeled 6, or 0.06. So 0.06. And we're going to triangulate to give us two values. Okay. So when we look up 0.91, we're going to come down to 0.9, and we're going to come across to the column labeled 1, which gives us a value of 0.8186. So when we look up 0.91, we get 0.8186. Okay. And when we look up 1.86, okay, when we come down to 1.80, so 1.80 is here, and when we come down the column labeled 0.06 to give us 1.86, we get 0.9686. So So 0.9686. Okay. In other words, and we know when we look up these values, these give us areas to the left hand side of the value that we looked up. So when we look up 0.91, we get a value of, which we're being told that the area to the left hand side of 0.91 is 0.8186. And when we look up 1.86, we're being told that the area to the left hand side of that, all the way down to negative infinity, is 0.9686. Now what we can actually see here is if we take the shorter line away from the longer line, we're left with the area between those 2 points. In other words, the area between here and here is the shorter line taken away from the longer line, okay, or the longer line, 0.9686, minus the shorter line, which is 0.8186. And when we do that particular calculation, okay, so we have 0.9686 minus 0.8186 gives us a value of 0.15. Okay. In other words, the area between 0.91 and 1.86 is 0.15. Okay. So what we know now is that this area here represents the probability of observing a z-score, yeah, that's greater than 0.91, okay, and that's less than 1.86. Okay. Now we know through our transform that this probability is equivalent to the original probability that we require. In other words, the probability of randomly selecting a factory worker and that they earn more than 692 euros or less than 725 euros is equivalent to the probability, yeah, associated with I suppose observing a z-score, okay, the probability of observing a z-score that's greater than 0.91, okay, and less than 1.86, okay, and the probability of observing a z-score that's between 0.91 and 1.86 is equal to 0.15. Okay. In other words, if we were to randomly select a worker, okay, and continue to randomly select workers from this particular population, that we would observe factory workers that have average earnings between 692 euros and 725 euros about 15% of the time. Okay, so that concludes this particular short video, okay, on the calculation of, I suppose, of what we have defined previously to be type 3 probabilities. Okay. They're probabilities where you have to calculate the area between two positive bounds, okay, on our z curve. Okay, guys, I hope that was informative. My name is Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland. Okay, thank you.